right, party people, let's talk about equilibrium. Okay, so snowball fight, you're doing that in class, blah, blah, blah. Key things are that reactions can go forwards and backwards. So we can go from reactants to products, but did you know we can also go from products to reactants? So instead of writing it like this, we just write a double arrow that indicates this is an equilibrium reaction. Technically, every single reaction you've ever seen can go in reverse in theory. Some of them do go in reverse actively, and for some of them, the reverse reaction is just not going to happen, usually for other thermodynamic reasons, which we'll talk about in Unit 9. But we might say that this is more or less only going in one direction or the other, but plenty of reactions, especially plenty of interesting ones, go both forwards and in reverse. So for an example, we have evaporation and condensation of H2O. So we've got H2O liquid that is turning into H2O gas. That's the evaporation, but then we've also got the gas turning back into a liquid. That's the condensation. So if you leave water in a flask or just a cup on your desk, you're going to see, if you come back in a week, it'll be less water in there because some of it has evaporated. Some of that evaporated water, the steam, is also recondensing and going back into the water, the liquid form. But since it's an open flask, an open cup, as soon as it evaporates, all of these molecules just pew pew, they're gone, right? So they might recondense, but they might recondense like over here, in this little puddle you have sitting on your desk instead of in the flask. So this is an example of an open system. An open system means the reverse reaction isn't available in the context of the system, aka the flask. The reverse reaction isn't going to visibly occur within this flask. If, however, we close the flask, right, so we put a little cork in it, or you have like a coffee mug with a lid on it, then whatever water is going to recondense or whatever steam is going to recondense is in the same container, so it would be able to recondense. And you see these double arrows indicating that both directions are indeed happening. Eventually, some amount of eventually the rate of these two reactions become equal, so we don't see any amount changing. So initially, if there's 0 steam particles in the flask, we're going to see some of the water evaporating. Some of that vapor is then going to recondense, but eventually these two rates equal each other. So this is just a summary of open versus closed systems. There's a lot of references to the snowball fight activity we are doing in class this day, but suffice to say, evaporation and condensation of water is a perfectly serviceable metaphor. But let's make it more exciting. Let's talk about graphing these things. So we talk a lot about concentration, that's molarity. Remember, that's moles per liter. So if you start with some reactant, let's say that's the NO2 here. So we've got this NO2 converting into N2O4. And we're going to have a coefficient of 2 here. And the reverse reaction is also happening. The N2O4 is breaking apart into 2 NO2s. Initially, if I only have this reactant, I start with 0.08 molar of NO2, and I start with 0 N2O4 in this container, this closed system. Initially, this is going to start converting into the product. It's going to start reacting into N2O4. So we see the NO2 going down, and we see the N2O4 starting to go up. Right? These rates right here are really steep. We can see the slope of this curve is very steep, indicating that the rate is quite high for the forward reaction. But eventually this rate starts tapering off, right? We see the N2O4 concentration is not increasing as much. And then by the time we get to this time, whatever time B is, the N2O4 concentration is not increasing at all, and the NO2 concentration is no longer decreasing, right? The equilibrium reaction is still occurring, but there is no net change to how much in terms of concentration, aka the amount of reactants and products that we see. So one interesting thing is that it doesn't matter if we start with only reactants, or in the same reaction, if we started with only products into O4, starting with 0 of the NO2, we would still see the same equilibrium position, that after some time B has elapsed, I'm going to see both of these concentrations stop changing. But it's important to note that the concentration is not equal for both of them, right? This has a concentration, I don't know, maybe that's like 0.035, and the NO2 stops at about 0.01 or something. They're not identical, but they have just stopped changing. However, when we talk about the reaction rate, this is a very important distinction. So I've got these two graphs right here. The one on the right is what we were doing, concentration in terms of moles per liter, that the concentrations eventually stop changing, but they are not necessarily equal to one another. If we graph the rate of the forward versus the reverse reaction, when equilibrium is reached, they are by definition equal to one another. When the forward reaction is faster, so like right here, at this time, the forward reaction is a higher rate than the reverse reaction is. So I'm going to see these things starting to close the gap to reach equilibrium. Once they have reached time B, wherever this occurs, the rates equal, and at that point, I see no net changes in the concentrations of either reactants or products, and that's what we see over here. But again, the rates are by definition equal. Okay, so the previous graphs talked about molarity, moles per liters. When we're talking about equilibrium, that's primarily what we're going to do, because we're going to be dealing with a lot of aqueous solutions, meaning dissolved in water, but we also are going to be dealing with gases a lot. So we talk about partial pressures when we're indicating the amount of a gas. Remember that pressure just tells us how many collisions with the container you have. So more particles, more concentration, well, you're going to have more collisions. So pressure and concentration are pretty, they are directly proportional for a gas. Sometimes, and that's usually going to be in atmospheres, although technically you can have kilopascals or torr as a unit of pressure. We don't really see those in this class. You can, however, still measure the molarity of a gas, and sometimes you'll see that, and that's perfectly serviceable. So just pay attention to what you're talking about. If you're talking about aqueous solutions, you're definitely not talking about pressure. If you're talking about gases, you could be talking about pressure or molarity. Just kind of depends what is the information given and where do you want to go from there. Okay, so we've got a little reaction right here. A plus 2B turns into C and D. Initially, we start with 1 atmosphere of A and 1 atmosphere of B, and we start with no C or D. So let's just call this 0.1. That's 1 ATM. And initially, I've just got 1 atmosphere of A and B. A and B. Well, let me make B a different color. Let's make this B. So it's at the same point. That's B. Okay. When we reach equilibrium, there is 0.8 ATMs of A. So I'll call that here. So let's say we reach equilibrium, like, I don't know, right here. This is where we reach equilibrium. And we'll say this is where A reaches equilibrium. And we're going to be sketching all the things in this graph. So firstly, let me just connect A. So it's starting here, it starts to go down pretty steeply, and then it will even off until the pressure stops changing. For B, however, it has a coefficient of 2. That means for every 1 atmosphere of A used up, 2 atmospheres of B use up. So if this is 0.8, then that means B at equilibrium is going to be 0.6. So about here, this is where substance B will end up at equilibrium. So it's going to have a steeper drop off until it also plateaus out. And we sort of get this plateauing of concentration for substance A and B. Now, for some different colors, we've got C in blue, and I'll do D in green. So as soon as these two start changing, both of them are going to go up by the same 1-to-1 coefficient as the substance A. So they'll be going to 0.2 molar, because 0.2 atmospheres, because 0.2 atmospheres of A were used up, so that means 0.2 atmospheres of C and D were produced. So eventually, this is going to be where D ends up, and it's also going to be where C ends up. So it's increasing and then it's tapering off. And I'm just kind of mimicking the line for C. Imagine they're just right on top of each other. Okay, and there we have it. Okay, this is a pretty straightforward set of questions. Write the equilibrium reaction. So freezing and melting, that means we're going from a liquid to a solid. Freezing, right? That's liquid turning into a solid, but we're also showing it as an equilibrium reaction where we're seeing the melting process occur too. So we put that reverse arrow. For the dissolution of a solid, remember dissolving means turning something into aqueous ions. So I'm going to separate this into its ions, sodium plus and hydroxide minus. Since they are now aqueous, since they are dissolved, we're going to write aqueous on them, but this is equilibrium, so we're going to write the reverse reaction. Those dissolved ions are also precipitating back out into sodium hydroxide. And then lastly, synthesis of hydrogen and oxygen gas. So that's going to be H2 gas and O2 gas forming water. I think you get the idea now. Let's see, we'll need liquid, coefficient of 2, coefficient of 2. Really nothing crazy here, just use your double arrows. Okay, getting into the second topic, the direction of reversible reactions, which is another way to say equilibrium reactions. What is happening when we start a reversible reaction is that as equilibrium is approached, and that's a phrase we use a lot, as you approach equilibrium or as you are trying to establish equilibrium, one reaction's rate will be falling, the other reaction's rate is increasing until they are equal. So recall some of our kinetics notation. This is the differential rate law. Rate equals K times some concentration, if it's first order, whatever. We're just using the rate F and the rate B, so forwards and backwards. And eventually, equilibrium is reached when those two are equal. So rate of the forwards will equal the rate of the backwards. But it is important to note that the constant for these might be very different. So just because the rates are the same does not mean that the actual concentrations of these are the same. And hopefully you see that from the previous graph, right? Equilibrium is reached, the rates aren't changing anymore when we get to this point, but they ended up at totally different pressure values from one another. And that's okay. That's part of it. This is another way of expressing that. Yeah, we see K subscript R here, R instead of B, reverse instead of backwards, but generally speaking, when we have a reversible reaction, an equilibrium reaction, one direction is favored. So that means you're going to end up with more of that direction's output than the unfavored reaction. So let's say you have something with a forward reaction is favored. What does a forward reaction do? It makes products. So if you're making more products, when you reach equilibrium, you're going to have greater concentrations of products than you will reactants. The reverse is true. If the backward reaction is favored, so thinking of our evaporation and condensation of water, if the backward reaction, aka gas condensing into a liquid, is favored, well, that is making reactants. So if that reverse direction is favored, you should end up with more reactants. The reactants will exceed the products in terms of concentration at equilibrium. And then every now and then you do have equally favored reactions, but it's pretty rare. Don't worry about that. It's a theoretical possibility though. Okay. So when do we have more reactants or more products? So we saw a couple different things in the snowball activity. things that shifted the position of equilibrium, and that's something we say a lot, the position of equilibrium. I'm not really gonna go over this, just thinking of moving the snowballs from the reactants to the product side. When we add more snowballs, more crumpled pieces of paper to, the group on the left, that's more snowballs you then can chuck over to the right. So the equilibrium position shifts to the right, or vice versa. Another way to say this is the forward reaction is favored. The other thing we can talk about is when you've already reached equilibrium, but then you stress the system in some way. So you give one side of the reaction more material, more of a certain compound. Then the position is out of whack and it wants to re-equilibrate. So that means moving in the opposite direction, so favoring the opposite direction's reaction until you reestablish equilibrium. So imagine we had reached equilibrium in the snowball fight, and then I just suddenly give a bunch more extra snowballs to one team. Well, those are going to get used up. Those are going to go to the opposing side to reestablish that equilibrium. Okay, so here's our example. We've got N2 and H2 in equilibrium with ammonia in H3. It's at equilibrium. When we think of the rates of the forward and the rates of the reverse reaction, if we add NH3 at some time t, when I say what happens, I just mean, does it go up, does it go down, does it stay the same? If you have more NH3, so more NH3 means more product to use up. If you have more product to use up, that means you're going to favor the reverse reaction. Favor the reverse reaction until you've used those products up enough to reestablish equilibrium. Favor the reverse reaction, so reverse reaction rate increases. And the forward reaction rate is going to decrease. Until they reach one another again. Okay, got one more example here. This one is just giving us moles of different substances in a flask. So we're given a starting value, so 0.4, this is substance A, and 0.5, this is substance B. And then we're told nothing else is in the container, and at equilibrium we end up with 0.15 moles of C. So we'll call that C. So I know that eventually I'll be reaching C. So I'm just gonna sketch that and then write this as a straight line, okay? Looking at the coefficients, if I made 0.15 moles of C, that means I used up 0.15 moles of A. So that means A should end up at, let's see, 0.25. That would be right about here. That's A. So it's stabilized there. And then I will go down to it. And then lastly, B has a coefficient of 2. So that means B is not using up 0.15 moles, it's using up 0.3 moles. So it starts at 0.5, so we should end up at 0.2. So this would be where substance B ends up plateauing. And again, we're just looking at the stoichiometry of this to determine how things get used up. Okay, so these are not super precise graphs. I'm just trying to show a little bit of the stoichiometry as well as the, whatchamacallit, fact that concentrations eventually equal out. Okay, I think I'll call it there.